Hey everyone, my name is Sachin. I'll be presenting Lab 5 now. So the goal of this lab was to choose our own adventure by picking a system of interest to us, and then getting our own data, and then predicting the outcome of the investigation with the aid of Python. So I wanted to investigate whether energy was conserved in a bow and arrow shot. See, the bow actually acts as a spring, so I wanted to see if all the spring potential energy and the gravitational potential energy was converted into kinetic energy. So in Python I found that it was, which is the ideal model, but in real life it didn't. So let's find out why. So here's basically my experiment. My point of mass was the back of the arrow, and the origin was set to be at the bow. From tracker we got our position data, which was the most important, so we can get our velocities and whatnot. And one thing I need to point out is that my arrow hits the trash can in this, but in the model there's no trash can, so it travels a little bit farther. But that doesn't change our delta k or delta u values at all. So solving for k was a little interesting. We had to use known forces such as gravity. First thing I did was I rearranged Hooke's law and set it equal so we can solve for k. Then we used gravity, so negative mass times gravity. So I hung a mass on the bow and measured the displacement from 0.26 to 0.18. And so we have the mass here, we have gravity, and then we solve for k, which is 176.4 newtons. So just like the spring mass lab, we had to provide Python with k and L sub naught. L sub naught is just relaxed onto the bow, and k I'll find in just a moment. For the gravitational potential energy, I measure the mass of the arrow, and we already know what g is. The height gets calculated on its own from the initial starting vector that we got from tracker. And for the kinetic energy, we already know the mass of the arrow, and then, as usual, Python calculates the velocity force using the forces that we insert and then starting position. So let's start looking at our code now. So I created two balls right here. The first one represents the tracker motion, the second one is the model motion. The model motion is going to be red, and the tracker is going to be blue. The mass of both of them is 30 grams, or 0.03 kilograms. The initial position is the same. It's from the tracker file, and then the initial velocity is 0 because it hasn't been released yet. And then down here I created a spring that's going to launch the arrow. So in this part of our code I set t and delta t, and here I tell Python to read the tracker data so we can track the motion of the tracker data. And here I set my UG initial, my US initial, and my KI. So in this part of the code, we're just defining our interaction initialization, some of the important constants. So we know what G is, we know what the stiffness constant is, we know what the relaxed length of the bow is. Here, the ball L equals ball.2 pos, which is the arrow, and we're just going to give it direction and then calculate S as it comes off the bow. And down here, we're just defining the kinetic energy, the gravitational potential energy, and the spring potential energy for the first time. And then we're going to update it later on. So now we're going to our while loop. The time was 0.534, and I set it to t because I have to use it a couple places. This is our while loop, and I need to introduce what an if statement is. It's a conditional statement. So what this is saying is that I only wanted the spring to give a force only up until when the arrow is launched, right? So that's what I'm telling it to do here. Tell the spring only to apply force up until the arrow is released. And then I have give a direction, and it calculates the stretch and everything, all the good stuff. And then here is the spring formula, Hooke's law. So it's going to calculate the force. And down here, I'm telling it to apply 0 force after the arrow is actually released. So in continuation of our code, here we have F gravity. It's only in the y direction. Here we have F net, which is the sum of the spring and the gravity. Here we have the velocity being updated, the momentum principle we've seen very many times now. And right here is just simply the position update. Here I have arrows representing the gravitational force and an arrow at the beginning that's going to show us the spring force. Down here is just K and the potential energies, and I'm going to calculate delta K, delta UG, and delta US simply by subtracting the final minus the initials. And then I'm going to also get Python to print these values so that we can compare them. So let's watch the code run. So the yellow arrow that just came and disappeared was the spring force. The black arrows represent gravitational force that are always going to be there. And then the blue ball is the tracker data. So you can see that the trail is not perfect behind it because I didn't pick my point of mass perfect. The red line is very clean. So now let's go to the purpose of the lab, which was to see if the energy was conserved. It doesn't matter how far the ball moved as long as the energy was converted from the bow to the actual shot. So the delta U was negative 12.10 and the delta K was 12.4. And yes, the energy was conserved. You can see that it's basically converted over. The slight difference is because I didn't put in proper values into Python, because Python's only going to read the values that I give it. So like for initialization stuff, as in like the length of the bow and everything, I probably messed up a little bit. but overall the energy was transferred. But let's look at the real system now. So for the experimental data, we see that the total delta U is negative 10.54, and for the kinetic energy, we lost about a joule over. So why did we lose it? In our model data, we see that an ideal system existed because all the energy was conserved. In our experimental data, we see that we lost about a joule, and that the delta U and delta K values weren't the same as the model values. Why was this? It is because in a real system, energy is lost due to unaccounted forces such as drag force. Thermal energy was probably lost to the surroundings too, and human error definitely existed in small amounts as well. Measurements were not perfect, and picking the point of mass probably wasn't perfect as the arrow was hard to see as it was traveling close to faster than the frames per second of the camera. So on tracker, it was really hard to pick my point of mass. In conclusion, in a real system, all the potential energy is not converted to kinetic energy. Well, that was my lab, and thank you so much for watching.